It's been raining heavily for quite some time now, so there will be some disturbing noise. So I am apologizing in advance for that. Recently proved the very nice formulas for our arithmetic functions tau and sigma. Let us next see something not so nice about these functions. Let's consider these calculations. Consider the two positive integers 2 and 10. Say we apply the function tau on their product. That is tau of 20, this is 6. On the other hand, if you take the product of tau of 2 and tau of 10, you get something else, you get 8. We would have liked to have equality, but unfortunately that's not the case. The same is the situation with the function sigma as well. Sigma of 2 times 10 turns out to be 42. However, sigma of 2 times sigma of 10 is not 42. So we get this nasty fact that in general these equations, which look very nice, are not true for the functions sigma and tau for all positive integers m and n. In spite of this, we can salvage matter to some extent with this new definition. Definition 6.2. A number-theoretic function f is said to be multiplicative if this equation is true, which did not turn out to be true for the functions sigma and tau. I mean, at least that's what we initially thought. But there is a condition. Whenever the positive integers m and n are relatively prime, under that condition, if this happens, then we would say that our number-theoretic function f is multiplicative. Now, our aim in this video is to prove that in spite of not having these equations true in general for all positive integers m and n, actually they turn out to be true with this extra condition, and hence the functions tau and sigma are multiplicative. But before we go to that, let us see two very easy examples of multiplicative functions. And those examples are these two functions. The first one is the constant function 1 at every positive integer n. We are calling it f. F of n is 1. This is multiplicative in a very trivial manner. You take any two positive integers m and n which are relatively prime. F of mn is 1. But at the same time, f of m and f of n individually, both of them are 1 and their product is also 1. So that way this equation is true for this particular f. And similarly, you can verify that this other function, the identity function on the set of positive integers, g of n equal to n, is also multiplicative. Next we can extend the definition of multiplicative function into a property of this type of functions. Suppose f is a multiplicative function and n1, n2 up to n are, say these are pairwise relatively prime positive integers, which means that if you take any two distinct elements from this list, they are relatively prime positive integers. Then f of their product is equal to the product of their individual f values. It follows by induction. Okay. And the definition of a multiplicative function is extremely straightforward to establish this by induction. So as a base case for the induction, you will take the case where there are only two relatively prime positive integers and then you extend that. Okay. So you have this somewhat useful fact about multiplicative functions for a general product which has not necessarily two relatively prime positive integers, but a number of them. Next, an application of this thing, this observation, you can find here. Say again f is a multiplicative function, and now you consider a positive integer n whose prime factorization is given. Then in this product, these individual prime powers are pairwise relatively prime because they consist of distinct primes, And that is why, by this observation, f of n equals the product of the f values of these individual prime powers. So this way we see that if we know the values of a multiplicative function at only prime powers, that's enough for us to calculate the multiplicative function at any positive integer. There is something else about multiplicative functions as well. Next we see that. Let f again be a multiplicative function that does not vanish identically. This means that f is not the constant function 0. That is, f is non-zero at some positive integer. So there will exist a positive integer n such that f of n is not equal to 0. Then f of n, you can write n times 1 in place of n. Now no matter what n is after all a positive integer, it can be anything. N and 1 are relatively prime, and because of that, and since f is multiplicative, so f of n times 1 is f of n times f of 1. Now we can cancel f of n from both sides because f of n is non-zero, and that gives you this fact that a non-vanishing function which does not vanish identically, perhaps I should not say non-vanishing because f may be 0 at some places, we don't really know, but which does not vanish identically, f of 1 has to be equal to 1. Next we have our theorem for today. The functions tau and sigma are both multiplicative. So let's see the proof. So the proof naturally starts by considering two relatively prime positive integers m and n, and we have to prove that these two equations are true for m and n, general m and n of this type. Now if m is 1 or n is 1, then of course these two equations are true, and that too in a very easy manner. That is because sigma of 1 is also equal to 1 and tau of 1 is also equal to 1. And why that instantly tells us that these two equations are true in that case, that I am leaving to you. It's absolutely easy. You just have to write the two equations if m is 1 or n is 1 in those cases. And you will see that it just is a very easy equality. So now we can consider the case where m and n are both greater than 1. What shall we now do? Since m and n are both greater than 1, so by the fundamental theorem of arithmetic, each one of them has a unique prime factorization, where if you take the same primes together, you can write them in canonical form like this. You already know this thing. Okay, so let the prime factorization of m be this, where we have these primes, these pi's, and the positive integer exponents, the ki's. Similarly, we have a prime factorization for n, where the primes are the qj's, some q's, and we have these j's, positive integer exponents. Now, because m and n are relatively prime, there is no common prime in these factorizations, in the sense that whatever primes you find here, you won't find there, and the primes that you have here won't appear here. And that is why the prime factorization of the product mn is just this, because these are different primes. And not just that, because of the way we have written each factorization, these distinct pi's are also different. Okay, no two of them are the same. So whatever primes you see here and their powers, all these are distinct primes. So now we have the prime factorization of mn. So we can apply our already proved formula for tau and sigma to this prime factorization of mn, and let's see what we get. Okay, so tau of mn will be obtained by what? What is our formula for tau? We have to add 1 to each exponent and take their product, which for mn is this entire product. But in this product, if you consider only these factors which have the k's, then you get tau of m, because These are the exponents that appear in the prime factorization of n. Similarly, this second part gives you tau of n. That's it. Next, let us see what happens to sigma. For sigma also same thing will happen. Sigma of mn, if you use the full factorization of mn, would involve these factors. So we take into account every prime that appears there. So p1 to the power k1 plus 1 minus 1 divided by p1 minus 1, and similarly the other factors involving the other primes. And in this entire product, if you only consider the first r factors, that is sigma of n, and the remaining factors give you sigma of n. So that's how we have proved that sigma and tau are multiplicative.